All right, welcome everybody. So we have a question about 6.2, number 13. So let's go ahead and take a look at that. And I was just talking to people at the beginning of class mentioning that at the beginning of our course page, I've got the reviews for the different exams. Exam 1 review includes now a copy of our first exam and the practice problems that I distributed for that. So you might want to take a look for that to review for that, the first bunch of material that we covered. If you have your first exam, then you can use that as a study guide because you can see my comments on the grading. If not, you can download a copy of it here. If you didn't get your first exam back, there's nothing I can do about it because it's in my office and I can't go on campus to get it. So you'll have to rely on that. And then there's a section to review for the final exam, just key topics that that I think you should focus on. Make sure you know how to do all of these things for the final exam. Okay, so we're looking for now I forgot the question that was asked. Let me see if I can find that. 6.2, number 13. Okay. So section 6.2 right here. Number 13, the last one. It's probably more challenging. Come on, number 13. Where are you? All right, let f of xy be this vector field. And let R be the rectangle with these vertices. Compute the flux of F across the rectangle. Okay, we worked through an example very similar to this, I believe, in class. Although I don't think I did it as a flux integral. I think we just did a normal line integral where we did it over a rectangle. So what we did for that problem was that we took that rectangle and we just broke it up into 4 separate line segments. Okay, so we wrote the integral as a sum of integrals over each line segment individually, and so that's what you have to do here as well. So we're going to have to break up this integral across each line segment. So we're going to have to parameterize each line segment of the rectangle. Okay, so let's go down to the paper and we'll see what we can do here. What did the problem say? The problem said that the vector field was given by negative 6x, comma 4y, and R is the rectangle with vertices 0, 0, 6, 0, oh, 6, 6, and 0, 6. Okay. And so what we're going to do is we're going to parameterize this rectangle. So we're going to find a parameterization for this curve over here. All right. So let's call that R1. And then we'll find a parameterization for this curve over here. Let me call this C1, and the parameterization will be called R1. So we'll parameterize it R1 of t, okay? And this will be C2, and we'll parameterize it by R2 of t. All right? And this will be C3, and this will be C4, and R3 and R4, right? So if I want to parameterize this first line segment of the rectangle, I need to write down just a straight line. I need to parameterize a straight line that goes from this point to this point. So I just need the x-coordinate to increase from 0 to 6. So I think the easiest way to do that is to write down R1 of t to be 6t, comma 0. That will work. Where t ranges from 0 to 1. When t is 0, we'll have the point 0, 0. And when t is 1, we'll have the point 6, 0. Okay, so that'll do it. By the way, if you had this one's probably pretty easy to see why that works. If you had more general points, if you say you wanted to go from point P to point Q, and you wanted to parameterize the line segment that joined these, what you would do, if you remember, we talked about this way back in chapter 2, I think. You find the direction vector. You find this vector v, right? And you can write down an equation of the line that goes from here to here by just viewing these as vectors. And by the way, when you do that, v is just q minus p, right? And the line r of t will just be the starting point plus t times this vector. And that is actually what we did here, okay? If you use this methodology, it will produce this. Okay, so you can go ahead and try that. But I think in this case, you can probably just kind of see that this works. But if you want to do it in more generality, this is how you do it. This is how you parameterize a line segment between any 2 points. Okay. Then what we need to do is we want to compute the flux around the rectangle. So that was f dot n ds, where n is the unit normal vector. But we also said that this is the same as what did we write? I'm going to have to look back at my notes just to make sure. I think I know what it is, but I need to make sure that I write it correctly here. So let me just take a peek at what we had here. N divided by the magnitude of n okay, ds, which was the same as the vector field evaluated at r of t and then dotted with n of t dt. Okay, this is what we'll be using. Okay, and we actually derived, I think in the video I showed how to get from how this becomes this, right? So this is the unit normal vector. Now this is a normal vector, but it's not the unit vector. This vector here is the vector, it's normal, but it's not unit normal. It's y prime of t, comma, x, negative x prime of t. Oof, that's curvy, this is angular, okay. That's what n of t is. And that will always produce, so x of t and y of t come from here, right? This is x1 of t, this is y1 of t. So if you do this, you'll always get a vector orthogonal to this one. And you can check it. If you just take the dot product of this with this, you get 0, right? So this is guaranteed to be orthogonal to this. So this is a normal vector. Okay? So that's where that comes from. And when you rewind this, we're dividing it by its length. So we're actually getting a unit normal vector. And that's how you compute flux. This is flux here. Flux is the vector field dotted with the unit normal vector to the curve at every point. Okay, and what you're doing is you're measuring how much of that vector field is pointing outwards of this curve. Okay, so, and what we're doing is we're breaking this apart into pieces. So what we're going to do is we're going to write this as the integral over C1 of this stuff plus the integral over C2 plus the integral over C3 plus the integral over C4. These individual pieces of this rectangle. So I'll just work through the integral over C1, all right? And then I'll let you do the rest. So we've already started it. We've already parameterized C1. This is our parameterization. So that first integral is just going to be this stuff, right? Notice I put a circle here because this is going all the way around the rectangle. This one's not. It's just going around one line segment. That's why I don't put a circle here. That circle just means it's a closed path. So we need to compute f of r of t for C1. Okay, so let me just write that down, what we're doing here. Okay, f of R1. Well, our vector field is this, and I'm plugging in this. So the x is right here. So this is going to be minus 6 times 6t. So it's going to be minus 36t. And then it's going to be 4 times y, and y is 0. So the y component is 0. So that's this guy right here. And I'm going to dot that with n1 of t. All right, so we have to dot it with another vector. How do I get n1? Well, we said that up here. It's y prime, comma, negative x prime. Okay, so here's my x, here's my y. So y prime is 0. Okay, so that's my y prime, comma, negative x prime. Okay, well, here's my x. X prime is 6, so it's going to be negative 6. Worked out easily this way, in this particular case, because I've got constants. All right, so I dot these together. Oh, look, I get 0. Very nice. So for this particular first part of our integral, we're just getting 0. For the other pieces, you may not get 0. All right, so it's something you're going to have to check piece by piece to see what you get. But what we'll do to finish, so we just finished this piece right here, C1. But now you have to do C2, C3, and C4 and add them all together. And what you get will be the answer. All right. So I'll leave it at that and let you finish up the rest. Oh, so there's a question about where does the 0, 6 come from? 0, negative 6, I think you mean. The 0, negative 6, so it came from this formula here, right? This formula here. This formula, we're taking f of r of t, right? So we got this, and then we're dotting it with n of t. Little n of t is given by this formula up here. It's y prime, comma, negative x prime. The y and the x are just, the x and the y are just the components of r. Okay? So all we're doing is we're taking the y component and taking its derivative, which in this case is just 0. So that's the y prime. And then we're taking negative of the derivative of the x component. So we're taking the negative of the derivative of this. So the derivative of this is 6. And so the negative of that is negative 6. So that's what this is. Right? This thing is just y prime, comma, negative x prime. All right. So other questions? Let me take a peek at the homework while you're thinking about stuff here. Yeah, that was in section 6.2. You've also got 6.3 and 6.4. I'll take you to the homework while you're thinking of other questions to ask. I want to point out something. In section 6.3, the very first problem, looks like this. Consider a vector field. And then they want you to determine, is it conservative or not, right? If it's not conservative, you're done, all right? You just hit submit at this point. Because it's not going to matter what you put here, all right? But if it is conservative, so you're going to check, then you're going to go through and find the potential function. And that's what it means to be conservative, is that it has a potential function. So if it's conservative, you're going to be able to find this potential function. Now, I want to point out that a potential function is like the antiderivative, all right? And we know that there's not just one antiderivative to a function. There's an entire family of antiderivatives. But the family is very simple. Any two elements of that family just differ by a constant. In this case, they're calling the constant k. And that's why there's a plus k here, okay? So what they want you to do is, I mean, there's an infinite number of answers you could put here if they didn't specify this condition right here, all right? So there's an infinite number of potential functions that would work, but they want you to find the one potential function, the only one that satisfies this condition, f of 0, 0 equals 0. Okay, so with this condition, there's only one potential function, and that's the one they want you to put into this box. The plus k illustrates the fact that to get from this potential function to any other potential function, you could just add a constant. And that's why they're writing plus k over here. So I just wanted to point out what that was about. Okay, so you're going to find the particular potential function that satisfies this condition, and that's what's going to go here. And this plus k means they're describing from that potential function how you get any other potential function. And if you use any of those potential functions, any of them, it will work. You can use that in the fundamental theorem of line integrals. It doesn't matter which potential function you use. So you could use the one with the k or without the k, it doesn't matter. You can just use what you put in the box here to evaluate this. And it should be very easy to do because the fundamental theorem gives you, it's a very nice theorem. It tells you how to do this integral very, very quickly, all right? So it's not going to be much work once you find the potential function. I think that's the hardest part. All right, let's see what we got here. No more questions? All right. I'll go peek through some of these other homework problems, see if I have anything else to say. No, they mostly look similar to that one in this section. Okay. Here we have some stuff on Green's. This is the next section, 6.4. This is about Green's theorem. We talked about that in the last couple lectures. Here's going to be a problem similar to the one we just did for flux. Here we have to do an integral around a rectangle, right? So you're going to do this one the same way. You're going to break it down. Except you don't have to do that. Wait, sorry. We're using Green's theorem. So actually, you don't need to do that in this case. Right? If you were doing this as a line integral, that's how you would do it. And you could do it that way. But there's a much, much easier way to do it if you're using Green's theorem. Green's theorem tells you that you can turn this into an area integral. And when you turn it into an area integral, you don't need to break it apart into pieces. So keep that in mind. Keep that in mind. When you do this line integral here, you don't need to chop it up into little line segments because we're just going to integrate over the whole rectangle. So it'll be much easier. Much, much easier. I see there's a chat question coming in. I'll take a peek in a second. Yeah, and a lot of these are similar to the problems that we did in class. So I think you should be okay with this. Make sure that you check these videos up here. Well, you don't have to. I mean, try it on your own first. But a lot of these videos cover a lot of the cases that you'll be seeing in these problems. Okay. All right, let's see a chat message coming in. Let's take a look at this. Oh, can I find in the problem that we were working on? as the example, can I find the third line segment? Sure. Okay, and what were we looking at? We're looking at 6.2 number 13. So let's go back to 6.2 number 13. All right, it changed. We'll use the one I had written down before. It was minus 6x comma 4y, and it had different vertices. All right, so we'll use the one that I had written down. So we had a question about coming along this direction on C3. Okay, so for this part, that's doing this guy. Okay, we're going to do the integral over C3 of f of R3 of t dotted with N3 dt. Okay, so that's going to be the integral along C3. Okay, now we have to parameterize R3 of t. Okay, so here, what are we doing here? We're starting at 6, 6, and we're ending up at 0, 6. All right. So what I would use for parameterization here would be, it looks like 6 minus 6t comma 6 would work, where t goes from 0 to 1. When t is 0, we start at, this will be 6, 6, and when t gets to 1, this will be 0, 6. So that will take us from here to here. Okay. So we also need to find this n. So it's going to be y prime comma negative x prime. Right? So we can write that down here. Y prime, 0. X prime, negative 6. So negative of that is positive 6. Right, so that is the normal vector that's pointing up this way, 0, 6. And we're going to dot that with the vector field to get how much of the vector field is flowing in that direction across the curve. Okay, so we're going to take the vector field evaluated here, all right? So at R3. So what was our vector field? It was negative 6x comma 4y. So negative 6 times x, so it'll be negative 6 times this. So it'll be, okay, negative 6 times 6, negative 6t is 36t. And then negative 6 times 6 is negative 36. So that's my first component. And then 4y. So that's going to be 4 times this, which is 24. And then I'm going to dot that with n of t. This is actually, I should call this n3 of t because it's different than the n1 of t, right? n3 of t is going to be 0, as we said, was 0, 6, right? And so here I'm getting something different than before. I'm getting, well, when I dot these, I get 0 plus 6 times 24. So 6 times 24 is 144, I think, right? So this is going to be the integral along C3 of 144 dt. Okay. Now, when we do this, I really should have. When I went to the DTs, I should have specified the bounds and the endpoints of my integration, right? So 0 to 1, right? So this thing actually ends up being 144 if I integrate that from 0 to 1. So yeah, you don't get 0 here. Okay. Are there other questions? Aha, I see. Yeah, so you forgot the 6 there. Okay. All right. Okay, I'm not seeing any other questions. So here's what I suggest you do. Just take a look here at the, for next time, for tomorrow. Take a look up here through these topics in the review for the final exam, okay? And see if there's anything you want to review, right? And you know, when you look at these, when you pick a topic, what I recommend you do is go find it in the homework and go practice some problems like that. Like find where there were homework for section 2.6, like maybe here's one. So you can go and practice it and just see how you can do, right? So refresh your memory on it. Maybe you'll answer your own question. If you still have a question about it, then we can discuss it on Thursday, okay? So we can discuss any one of these things. But you should be prepared for any one of these topics to appear on the final exam. Obviously, I can't put all of these on the final exam, so I'm gonna have to pick and choose. I'm certainly gonna pick stuff from here, from chapter 6, because we haven't been tested on it yet, right? So you can bet on Green's theorem. That's definitely gonna be on the final. Fundamental theorem, I mean, look at it, it's called fundamental. gotta put that on the final. Actually carrying out a line integral, I think that'll be on the final. So certainly, I'll go in and make those bold, all right? I'll make a note of that. These will certainly be topics on the final exam, okay? And maybe something about vector fields as well. Maybe I'll put a problem. I'm not sure what I'd do. Maybe have you sketch a vector field? I think there were some exercises like that. That might be good. So certainly stuff in here is going to be, you can count on these sections to be on the final. I'll have to pick and choose though from this material. I can't put everything. So probably I'll try to evenly distribute questions, you know, pick questions evenly distributed throughout these sections, okay? So look through here and see if you have any questions about this stuff. All right. So I think we'll call it today, and I'll just answer questions on Thursday, okay? All right, so I'll say goodbye.